Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture we were discussing about hydrologic design. We have stopped with the topic of risk analysis. Today we need to solve some numerical examples on risk analysis. In addition to that, we have to solve some of the examples on probability distributions also. These different types of distributions we have studied in the previous module. That time I did not work out the examples related to different probability distributions, because I wanted to give you some idea about the return period, probability of exceedance, all those things. So, today we will combine the numerical examples on probability distribution and also risk analysis. Let us start with solving the examples. First example is on probability. The annual rainfall data for a period of 12 years is listed in the following table. 12 years annual rainfall data is given to you. Find the probability that the annual rainfall in any year will be greater than 1000 millimeter, less than 1000 millimeter and between 1000 and 1150 millimeters. We need to estimate the probability related to different conditions. One is related to annual precipitation or the annual rainfall less than 1000 millimeter, second one is greater than 1000 millimeter, and the third one is the rainfall value between 1000 and 1150 millimeters. Here we do not have any distribution and any other details. So, we will make use of the probability expression by number of events divided by total number of data in the sample. The probability of occurrence of an event is nothing but P is equal to M by N. M is the number of events which are satisfying the conditions and small n is the total number of sample data. Here in this case it is 12. These are the data corresponding to annual rainfall. Annual rainfall data in millimeters for 12 successive years. We need to find out probability that the annual rainfall in any year will be less than 1000 millimeters. So, here we can count how many events are there representing the value less than 1000 millimeters. So, here we are having corresponding to second year it is 995, fifth year it is 900 and 9th year 990. These are the three events which are less than the given condition. So, small m is 3 and small n is 12. So, we can calculate the probability by using the formula P is equal to m by n 3 by 12, that can be calculated as 0.25. Now, the second part is to find out the probability for the events corresponding to the value greater than 1000 millimeters. Probability that the annual rainfall in any year will be greater than 1000 millimeter. So, here three events are less than 1000 millimeter and we are having total events. So, remaining events will be greater than 1000 millimeters. Here in the data points we do not have any data corresponding to rainfall is equal to 1000 millimeter. If that case is there, that we have to exclude if we are calculating the probability of occurrence of events greater than 1000 millimeters. So, here in this case that is not there. So, remaining events which we have calculated 3 as rainfall less than 1000 millimeter, remaining 9 events will be representing a value greater than 1000 millimeters. So, we can calculate the probability as 9 divided by 12, that will be coming out to be 0.75. So, if you add these two probabilities, you can get equal to 1. Now, the third question is that probability that the annual rainfall in any year will be in between 1000 millimeters and 1150 millimeters. We need to count the number of events coming within this range, and then we need to calculate the probability. So, if we are checking the values, we can understand that the annual rainfall between 1000 millimeter and 1150 millimeters, if we check in the table, we are having corresponding to first year, third year, fourth year, then comes 6th year, 7th year, 10th year and 11th year. So, in total we are having 7 events which are coming within this range given, that is 1000 millimeters and 1150. So, the corresponding probability is given by P of x between 1000 and 1150 can be obtained by 7 by 12, that is 0.583. This is very simple problem to calculate the probability corresponding to different conditions given. Now, we will move on to second example. Second example is related to probability density and cumulative distribution functions. The probability density function of a random variable is given by f of x is equal to kx for x varying between 0 to 9 hours. X is between 0 and 9 hours. Determine the value of k and the cumulative distribution function. Also find the probability that the random variable takes a value less than or equal to 4 hours. So, here you can understand that we have been given with the probability density function. It is representing the continuous random variable. F of x, that is PDF, is given by kx and the range is also given to us. We need to determine the value corresponding to k, cumulative distribution function and also probability corresponding to a particular condition given in the question, that is x less than or equal to 4 hours. We need to calculate the value corresponding to k, we need to find out the cumulative distribution function, and third part of the question is to find out the probability that the random variable takes a value less than or equal to 4 hours. So, we will start solving the example. First, we need to determine the k value. Our probability density function is f of x is equal to kx. How can we find out the value corresponding to k? From the theory of probability, we know that integral minus infinity to plus infinity f of x dx equal to 1. This is corresponding to continuous random variable. If we integrate the probability density function within the limits minus infinity to plus infinity, it should be equal to 1. That is representing the law of total probability. So, here we can substitute f of x equal to kx and we can integrate within the range 0 to 9. It is given in the question that the PDF which is given, that is f of x is equal to kx, is valid for a value corresponding to x within the range of 0 to 9. So, this is a simple function, we can integrate within the limit 0 to 9, it will be taking the form kx square by 2. We can substitute the limits 9 and 0, it will be giving us the value of k as 2 divided by 81. The value of k is determined from the probability density function. So, our f of x will be taking the form f of x is equal to 2 by 81 x for x varying between 0 and 9. This is our probability density function. Once the probability density function is there with us, we can find out the cumulative distribution function. That is, one is the cumulative distribution function we can obtain by integrating the probability density function within the respective range, and if the cumulative distribution function is given to you, by differentiating that we will get the PDF. So, here PDF we have found out, we can find out this cumulative distribution function. Capital F of x is given by integral minus infinity to plus infinity f of x dx. Now, we can make use of our PDF here, that is capital F of x, CDF is given by integral 2 by 81 x dx. When we integrate this, we will get f of x equal to x square divided by 81. The range of x is 0 to 9. You can substitute the value 0 and 9 here and get the value corresponding to that. It will be coming out to be capital F of x equal to 1. In between, corresponding to in between values, that is f of x less than or equal to 4, less than or equal to 5, that way if you want to calculate, you keep the function as such, corresponding values of x can be substituted in this and answer can be found out. So, here I am keeping the function as such, CDF is equal to CDF f of x is equal to x square divided by 81. This is the way in which we will be finding out the cumulative distribution function from probability density function. Now, one more part is left, that is the probability corresponding to an x value less than or equal to 4 hours. That is the third part, probability that x is less than or equal to 4 hours. So, that is given by P of 0 less than or equal to x less than or equal to 4. So, we can get the value corresponding to it by integrating between 0 to 4 fx dx. This is by making use of the probability density function. We can compute it by making use of cumulative distribution function also. So, when we substitute for fx, that is 2 by 81 x, fx is 2 by 81 x, integrated within the limits 0 and 4. So, the function is 2 by 81 we can keep outside, x square divided by 2, 0 to 4. This will be giving us a value of 0.197. This is calculated by making use of the probability density function. Instead of PDF, we can make use of CDF also, we can find out the value, that is f of x is equal to 4. So, if we substitute in the CDF, CDF is given by x square divided by 81, x is 4, 4 square divided by 81, that is 16 divided by 81. So, we will get the same answer as that of 0.197. So, this is a simple example related to PDF and CDF. Now, let us move on to an example related to binomial distribution. We have seen different types of distribution corresponding to continuous random variable and discrete random variables. When we were discussing about discrete random variables, we have looked into two types of probability mass function. In the case of discrete random variables, we were using the terminology PMF. It was not PDF. So, here we are going to solve one example related to binomial distribution. A dam is having a design life of 50 years. Estimate the probability that a flood having a return period of 100 years will occur once and 3 times during the life of the dam. So, here we are having a dam which is having a design life of 50 years. We need to estimate the probability that a flood having a return period of 100 years which may occur once in this design period, and second part is which may occur thrice in this design period. This problem can be solved by means of binomial distribution because this is related to discrete random variable. I did not solve this at the time when I was discussing about binomial distribution because you were not familiar with the term of design period of a structure. That we have completed in the previous lecture only. That is why I have kept this question to be solved after completing that particular topic. So, a dam is having a design life of 50 years. You know what is meant by design life, and we need to compute the probability that a flood having return period of 100 years will occur once and 3 times during the life of the dam. So, here we are having capital N is equal to 50 years and return period is equal to 100 years. 100-year return period flood we are considering. and the probability corresponding to that will be 1 by t, p is equal to 1 by t, these two are inversely related. So, p can be calculated by making use of 1 by t. So, n is given, that is design life is 50 years and t is equal to 100 years. Estimate probability of exceedance. We need to calculate small p, that is the probability of exceedance. We can make use of binomial distribution to find the probability of occurrence, because the event exactly occurring r times in n successive trials. The number of trials we can consider as 50, because the design life period is 50. So, if we are considering every year, so we are having 50 number of times, and out of that r times the flood will be occurring. So, in such cases we will be making use of binomial distribution. Binomial distribution is given by NCR p to the power of r q to the power of n minus r. NCR is nothing but n factorial divided by n minus r factorial r factorial. So, here we need to identify different terms. N is given as 50 years and t is given as 100 years. Design period is 50 years, return period is 100 years. So, here we can substitute the values corresponding to n and r after finding out the values corresponding to p and q. So, p can be obtained as 1 by t. We know probability of exceedance is nothing but 1 by return period. Return period is 100. So, p can be calculated as 0.01, and what is q? Q is 1 minus p, that is 0.99. Now, we can substitute in the binomial distribution. For the first condition, n is 50 and r is equal to 1, that is the flood is occurring once. Now, we can calculate n minus r as 49. Now, you can calculate the value corresponding to P51, that is equal to 0.31, it is equivalent to 31%. So, the probability of occurrence of the flood exactly once in the design life period of the dam is calculated by means of binomial distribution. That was found out to be 31%. There is a 31% chance that a 100-year return period flood will occur once in the lifespan of the dam. Now, we can move on to the second part of the question, that is the probability of occurrence of a flood thrice in the lifespan of the dam. So, here in the second part r is equal to 3. There is no change as far as n and t are concerned. Design period n is equal to 50 and the return period t is equal to 100. So, there will not be any change taking place in the values corresponding to p and q, but only difference is there in the value of r is equal to 3. So, n is equal to 50 years, t is equal to 100 years and r is equal to 3 times. N minus r is 47. So, we can substitute in the binomial distribution expression and we can calculate the value as 1.2%. Occurrence of the flood thrice within that design period is lesser, that is 1.2%. There is a 1.2% chance that a 100-year return period flood will occur thrice during the design period of the dam. If it is once, the probability of occurrence is chance is more, and in the case of thrice occurring case, it is 1.2%. So, this is related to binomial distribution. Similar to the binomial distribution, we can solve other distributions such as Poisson distribution, gamma distribution, etc. Now, let me move on to the extreme value distribution, that is Gumbel's distribution. Extreme value type 1 is termed as Gumbel distribution. The annual precipitation data for a period of 12 years is listed in the following table. This is the same data which we have used in the first problem. From the analysis, it was found that the random variable follows extreme value type 1 distribution. Estimate the parameters of the distribution and the probability for the variable to exceed 1500 millimeters. So, here the data corresponding to annual precipitation is given to us. We are not going to check whether it is following extreme value distribution or not, but it is given in the question that it is following extreme value type 1 distribution, that is the Gumbel's distribution. We need to find out the parameters of the distribution and also probability for the variable to exceed 1500 millimeters. So, extreme value type 1 distribution, we need to have idea about the PDF and CDF. We have already made use of these distribution for solving one numerical example on frequency distribution. So, here let us relook into the distribution function. Probability density function is given by f of x is equal to this particular expression, and cumulative distribution function is given by f of x is equal to e to the power of minus e to the power of minus alpha x minus beta. So, here we have substituted for alpha multiplied by x minus beta minus alpha multiplied by x minus beta as y, that is the Gumbel's reduced variate. And alpha is the scale parameter which is greater than 0, and beta is the location parameter which is between minus infinity and plus infinity. So, we need to find out the distribution parameters, that is alpha and beta, and we need to find out the probability for the variable to exceed 1500 millimeter. Let us start solving the example. First we need to find out the parameters. Parameters alpha and beta, we are having the expression corresponding to that. Alpha is given by 1.28255 divided by s, and beta is equal to x bar minus 0.45005 sigma. These are the parameters of Gumbel's distribution. Here you can see one term corresponding to s and another term corresponding to x bar is present. So, s is representing the standard deviation of the sample data and x bar is representing the sample mean. So, first we need to calculate the standard deviation and the mean corresponding to the sample data. Then only we can go for the computation of alpha and beta. So, these are the data given to us. Now, we can compute the mean value by taking the average of these values given for precipitation. So, sample mean is given by x1 plus x2 plus up to xn divided by n. Here we are having data up to x12. So, we will be dividing it by 12. So, this can be calculated as 1070 millimeters. Now, next step is to compute the standard deviation, sample standard deviation. X bar is 1070 millimeter. Standard deviation is given by the formula s is equal to under root of 1 by n minus 1 sigma I is equal to 1 to n xi minus x bar all square. So, here in the denominator we are having n minus 1 because it is corresponding to the sample. If it is related to population, we will be using n. So, n is 12 here and we need to calculate xi minus x bar all square. So, xi is given by the precipitation corresponding to each year, I varies from 1 to 12. We can compute xi minus x bar, it is calculated over here in this column, and next we can calculate xi minus x bar all square, that also calculated. And after that we can get the summation of xi minus x bar square, and that can be substituted here in this expression for s. The sum of sigma I is equal to 1 to n, xi minus x bar all square is coming out to be this much. So, once we substitute for that value, we can calculate s as 106.49 millimeters. So, this is the standard deviation. Once we have computed sample mean and the corresponding standard deviation, we can move ahead for the computation of the parameters of the Gumbel's distribution. So, the parameters alpha and beta we need to compute. Alpha is consisting of standard deviation. Alpha is equal to 1.28255 divided by s. So, that is coming out to be 0.012. And coming to beta, beta is given by x bar minus 0.45005 sigma. X bar is 1070. It can be calculated as 1022.07. So, we got the values corresponding to different parameters of Gumbel's distribution. Now the second part of the question is to calculate the probability that the random variable exceeds 1500 millimeters. That is, our rainfall is exceeding 1500 millimeters. What is the corresponding probability? That can be calculated by using the formula Px greater than 1500. So that is obtained by making use of the cumulative distribution function. This is equivalent to 1 minus Px less than or equal to 1500. That is 1 minus capital F x is equal to 1500 will be giving us the value corresponding to the probability that the variable exceeds 1500 millimeters. So here we need to compute the capital F x is equal to 1500. We know the cumulative distribution function fx is given by e to the power of minus e to the power of minus y. What is y? Y is given by alpha multiplied by x minus beta. Here x is nothing but 1500, alpha and beta we have already calculated. Now we can substitute in the expression for y the values of alpha, beta and x. It can be calculated as 5.73. So y is obtained as 5.73. Now we can substitute the value of y in the cumulative distribution function f of x. So when we substitute y is equal to 5.73, it is calculated as 0.996. So the probability can be calculated Px greater than 1500 is equal to 1 minus Px less than or equal to 1500. So that can be calculated as 0.00323. The probability that the variable exceeds 1500 millimeter is very small. You can observe the data series itself, in that there is no data corresponding to 1500 millimeters. So based on the probabilistic distribution, when we calculate, the value is coming out to be very small. So this way we can make use of Gumbel's distribution to calculate the probability. For that, first we need to find out the parameters of the distribution. Similar way we need to calculate the case with the other distributions also. I am not solving the examples related to that. The methodology followed will be the same. Now let us move on to solve some examples related to risk. Let me first read out the question. The design life of a hydraulic structure is 100 years. Estimate the risk involved for this hydraulic structure if it is designed for 50-year return period flood and 200-year return period flood. Two cases are there. The design period of the structure, design life of the structure is 100 years, and we need to compute the risk in two cases. One for the case of 50-year return period flood, and the second one is for the case of 200-year return period flood. How can we compute the risk? The formula which can be utilized for finding out risk we have discussed in the previous lecture, that is given by r is equal to 1 minus 1 by t to the power of n. T is nothing but our return period, capital N is the design life of the hydraulic structure. The design life of the structure is 100 years, only the return period is changing in both the cases. N is equal to 100 years and T is equal to 50 years for case A. We can substitute that in the expression for risk. It can be calculated as 0.867, it is around 86.7%. So 50-year return period, if we are talking, there is a chance of risk of about 86.7%. Then coming to the second case, that is 200-year return period flood. While discussing about the risk factor, I was explaining that we need to choose the return period according to the importance of the structure. We will not be using the same return period for all the types of structures. So in the case of dams and other major structures, the return period which will be considered will be very high. So definitely you can understand that when the return period is increased to 200 years, the risk associated with that will be less compared to a return period of 50 years. So we can solve the second part. N is equal to 100 years and T is equal to 200 years. So, when you substitute in the expression for R, you can calculate the risk associated with that as 0.394, that is 39.4%. So, the risk is reduced. Here we need to have two data, one is the return period of the extreme event and also the design period corresponding to the particular hydraulic structure. Now, let us solve one more example related to risk. The design life of a particular culvert is 5 years. What is the design return period to be considered for the design of the culvert in order to accept only 10% risk that can be associated with flooding within the design life? Also, estimate the chance that the culvert designed for the above design return period will not have its capacity exceeded for 50 years. Two parts are there, slightly difficult to understand the question, read it carefully. We need to find out the return period corresponding to the design of a culvert which is having a design period of 5 years and we can allow a risk of 10%. That is the first part. By allowing a risk of 10%, we need to calculate the return period, and then next step is, second part is to find out the design period. Second part is to find out the chance that the culvert designed with the return period which we have found out in the first part will not have its capacity exceeded for 50 years. Let us start solving the problem, then you will be able to understand. In the question it is given that the design life of the culvert is 5 years. So, 5 years design life is there for the culvert. Those type of structures will be given less importance, that is why the design life is given 5 years and the return period considered also will be less in such cases. Here we need to compute the risk associated with the structure. N is equal to 5 years and risk allowed is 10%. We need to compute the return period corresponding to this allowed risk. We are having the formula for risk, we need to compute the return period T, and second part is to compute the risk. We are having the design life of 5 years and also for which return period the risk has to be computed, the return period which we are computing in the first part of the question. Two parts are there in this question. First part is to find out the return period corresponding to a risk of 10%, allowed risk is 10% and the design life is the 5 years. And second part is that if we are considering a return period of the one which we are calculating in part 1, how much will be the risk associated with that. We can proceed solving the question. Risk involved R is 10%, that is 0.1, and N is equal to 5 years. We will substitute in the formula R is equal to 1 minus 1 minus 1 by T to the power of N, and from this we can calculate the return period T as 47.98 years. As far as a culvert is concerned, this return period is very high, 47.98 years. And in majority of the cases, we will not be considering 47.98 years, we will be approximating it to 50 years. So, this is the design return period which can be calculated from the question for a risk to happen around 10%. There is a chance that 47.98 year flood will occur once or more in the next 5 years. Second part of the problem is to calculate the reliability. For that, first we will compute the risk associated with that. So, we are going to make use of new design return period, and in that case N will be 50 and T will be 47.98, which we have computed in the first part. 47.98 can be approximated as 48 years. And we can compute the risk associated with that. R is equal to 1 minus 1 minus 1 by T to the power of 50. So, T we have substituted as 48 and risk can be calculated as 0.65. 65% of risk is associated with this. but we have been asked to find out the reliability, that is the chance that the culvert designed for the above design return period will not have its capacity exceeded for 50 years. How can we calculate reliability? Reliability is nothing but it is 1 minus R, 1 minus risk, that is 1 minus 0.65, it can be calculated as 0.35 or 35%. So, these are the different types of numerical examples which can come under these topics. You need to try with different example problems and exercise problems. You will be getting different numerical exercise and example problems from these reference textbooks. Try to solve maximum number of problems related to this topic. So, here I am winding up the problem solving session on probability distribution and risk analysis. Thank you.